Welcome to this webinar today. It's my pleasure to introduce our speaker today, Professor Christos Georgakis. He is a distinguished professor at Tufts University in the Department of Chemical and Biological Engineering. He's previously a professor at MIT, Lehigh University, and NYU. He's a director and organizer of Future Innovation of Process Systems Engineering, a conference that's held every 2 years to discuss unsolved challenges in process systems engineering. He earned a Ph.D. from the University of Minnesota, a master's from the University of Illinois at Chicago, and a bachelor's degree from the National Technical University of Athens. He is a fellow of AIChE, American Association for the Advancement of Science, and IFAC. He served as president of the American Automatic Control Council from 2002 to 2003. His research activities focus on the development of data-driven modeling methodologies with applications in both batch and continuous processes. And we're going to hear a little bit about that today from his presentation. He has 7,760 citations of his work with an H index of 42. Now, we are honoring him today with this award, and in 2001, he received the Computing Award from the CAS division of AIChE, and this past year he received the 2022 CAS Division Distinguished Service Award. So with that, I'd like to turn it over to Christos for his presentation. Welcome, Christos.
Thank you, John. Thank you, everybody, for being in the audience. Let me start sharing my screen and start the presentation. I see a lot of familiar names. So the topic that I will discuss with you today, and feel free to ask questions through the chat room or at the end so that we have a dialogue. Purposefully, I am not giving you all the details that one can give in the presentation. I'm going to have some, you're going to sense some gaps. This would motivate you asking questions. The topic is how to design dynamic experiments and how to estimate data-driven dynamic models and to use them for the optimization of batch processes. But as I will say in the third part of the talk is how to discover the detailed stoichiometry of taking place in a batch reactor. So the background is that many batch processes are not well understood, and thus we cannot have a knowledge-driven model with all these details. But the dynamics are very important, and they often need to be optimized. The classical methodology of design of experiments, which is about 40 years young, does not deal with dynamics, and this is the main motivation for the description of today. Or the main message today, to some extent, is going to be first to tell you how to design dynamic experiments, and then how to develop dynamic models from the collected time resolved data during these experiments, and the type of such models we will call dynamic response service methodology models. And third, but not least, is how to use these data-driven models to understand the inner workings of the batch process, primarily when a reaction is taking place, and for which reaction network we do not know the stoichiometry. And nowadays, of course, there are a plethora of robotic devices which can be used to collect data. There are devices in which they can run more than just 5 or 6 batch experiments. Some of such devices could cost $1 million, and they can run several experiments in parallel. And of course, as a result of that, we have lots of data. Here is a set of data collected through 30 experiments. The duration of the data is about 13 days. This is a cell process, and if I remember correctly, this data is the viable cell density, which initially increases and then it decreases in the second phase of the cell process. This will be the type of data that I would like to model. And I would like to model them not only one experiment at a time, but at all experiments and at all times. And that's why it will be a dynamic model. So let's first talk about the classical methodology of design of experiments, in which one can have different types of designs: full factorial, fractional factorial, standard composite designs, aiming mostly to collect the largest amount of information about the unknown process with a limited number of experiments. These experiments, to some extent, in most cases, collect data at the end of the experiment, and the collected data then are used to estimate what's called the response surface model, a polynomial type of a model like the one indicated here. The main observation is that neither the design nor the corresponding model developed address the issue of dynamics, how to understand the dynamics of the process and how to model time-resolved data. So here we're going to discuss two generalizations of this classical methodology of design experiments and response surface models. The first is the design of dynamic experiments. Dynamic experiments are needed so that the operating conditions during, let's say, the batch process will not be invariant with time. It is expected that sometimes we might want to operate the reactor at a temperature profile that is not constant with time. Certainly, we can feed the bioreactor with nutrients, and we would like to vary the amount of nutrients fed into the unit with time. Or we might need to change the pH of the bioreactor versus time. And that's the need for trying to design experiments that are dynamic and vary with time. And of course, we're going to model these experiments. We're going to collect time-resolved data. And instead of modeling the classical response surface model that is indicated here in blue, one would like to develop what we will call DRSM model, in which dynamics are taking place. So these are the two key points that I will try to cover today. So let's first talk about the design of dynamic experiments. This schematic indicates, let's say, the possibility of running different experiments. As you can see, these different experiments might have different durations between maybe 10 and 15 days. And the variable that I'm changing here is the pH. In general, in order to design dynamic experiments, first one has to decide the domain within which the experiments are going to be taking place. And this domain is primarily consistent of a maximum profile with time and a minimum profile with time. And of course, the middle of this territory will be called the center point. And of course, the duration here is in terms of hours, a fixed amount of hours, 1 hour, 1 day, one minute, but of course the time can vary as well. With such definition of the design, one ends up defining a coded dynamic factor. In the usual design of experiments, one works with coded factors, not dynamic. Here we'll have coded dynamic factors. It is a variable that will characterize the operation of the experiment, and usually it will be normalized to range between -1 and +1, -1 being the lower value of the domain and +1 being the upper value of the domain. And the main idea and the main simple idea in designing dynamic experiments is to parameterize these operating conditions, Z as a function of dimensionless time tau, in terms of a linear combination of shifted Legendre polynomials. The first one, of course, is a constant polynomial. The second is a linear one. The third is a quadratic. And of course, one can have as many as you wish, as much complex profiles considered. But when you do so, then the number of coefficients that you have to specify and which will define the experiments will increase, and consequently, the number of experiments will increase. So here are some example time-varying profiles. These are the simplest time-varying profiles. These are 9 experiments in which the variation with time is considered only to be linear, and the domain within which these temperature profiles are defined is a rectangular domain. Both the bottom edge and the top edge are not dependent on time. These profiles, of course, could also be defined in a domain in which both the upper part and the lower part of the domain is varying with time. And in such a case, these same linear profiles will appear to be curvilinear in these more general domains, mostly because the width of the domain changes with time. There are several types of experiments that one can define, similar to the DOE experiments. So on the first, actually, these are 4 sets of experiments. On the first row, there are full factorial designs in which the dependence on time is linear. On the lower left window, we have quadratic profiles. And on the lower right window, we have cubic profiles. So in essence, you can define all kinds of profiles as it is appropriate for the problem that is considered. We can also define fractional factorial designs, and on the top graph here is the 1/2 fraction of the cubic profiles, and on the bottom is the 1/4 fraction of quartic profiles on the bottom that I have a polynomial dependence up to the fourth order. But in order to understand both the power and the use of these dynamic experiments, let us consider a very simple case, a case in which we have a reversible reaction, A1 going to A2, and we have defined a range of operating conditions between 40 and 60 degrees Celsius. First, we're going to assume that we know the detailed kinetics of the process. And by using the detailed kinetics of the process, we can calculate the model-based optimum. So you can see the model-based optimum is to operate the reactor at the top allowed temperature for almost, let's say, 0.4 hours, and then decrease it and operate it at the bottom allowed temperature for the last segment of the 3 hours operation of the reactor. The profiles are very simple. The reactant A1 is decreasing, the product A2 is increasing, and we can achieve a 65.2% yield to the desired product, B as I call it here, or A2 as I called it up here. These calculations were done by Dr. Pulsner at CMU using a software package that he has defined called Infinite Opt. Now let us see whether we can optimize the reactor without utilizing the kinetic model, without spending time to understand the kinetic model, but by use of these dynamic experiments. Here are some examples of experiments. Most of them start at the top corner because in most reactors you want to start at the highest possible temperature. And because of thermodynamics, you might want to decrease the temperature in order to take advantage of thermodynamics that they are more favorable at the lower temperatures. And we will do that without any knowledge of the kinetic model. And the big question is how close this set of experiments will bring us to 65.2% yield to the desired product. When I first started thinking about this type of an approach, my guess was, maybe we can do 40%, maybe we can do 50% yield. And maybe if I were to ask all of you to think and guess how much I can get without the kinetic model, you probably will not going to be that far away from this guess. So let's see how close we can get to 65%. To start with, we're going to have only three experiments, one at the top temperature and two linearly decreasing profiles, one decreasing all the way to the bottom temperature and the third one decreasing halfway. With these three experiments, we can calculate that the maximum yield is 63.44% plus or minus 3%. And we can compare it to 65%. So clearly you can see with only three experiments, we've come very close to the model-based optimum, which, to tell you the truth, when it first happened 10 years ago, it was a big surprise to me. You can do another set of experiments exploring quadratic profiles. In such a case, you can get 64.11 plus or minus 5%. This is the accuracy of the model developed because you are counting for measurement error. And of course, you can have 7 profiles exploring both concave downwards and concave upwards temperature profiles. And in such a case, we're getting almost about the same. All three sets of experiments bring us very, very, very close to the model-based one. To some extent, the three optimal profiles we calculated are depicted here. The dashed blue is the model-based one. The red straight linear line is the DoDE one with 3 experiments. The purple one is the optimum when we do 5 experiments, and the green one is when we do seven experiments. And what's striking here is that even though all these 4 profiles are quite different from each other, yet the yield that they give is not that different from each other, which to some extent indicates that the sensitivity of the optimum to the exact shape of the temperature profile is not that great. This was a simple example. Let me talk about a much more complicated example that I will call a Dow Polymerization Reactor. It is a really industrial operating in polymerization reaction for which they have developed a detailed kinetic model, which was used here to do the experiments. So we will pretend we have no kinetic model because we are not going to utilize the kinetic model for the optimization. And we will try to optimize the process. And the aim here is to produce the same amount of polymer, the same quality of polymer, but try to increase the total amount of polymer produced and thus increase the productivity. The desire to increase the productivity in the existing unit, of course, has substantial economical benefits because it does not necessitate the building of a second unit to meet the rising demand. And the way that we're going to do it is by changing the incoming flow rate of the monomer and by changing the temperature profile of the operation. And here are the experiments that we have performed. The black dashed line is the base case scenario, the way that the reactor is operating now, and is operating at a constant temperature, a little bit higher than 120 degrees C. And we designed several experiments in which we systematically increase the amount of monomer fed because we want to increase the productivity, so we have to feed more. And then we have to stop the reaction at an earlier time so that we can increase the productivity. And as you can see, the profiles of the monomer feed rate are so designed so that they are decreasing at the very end of the feeding period. This is because we want to allow the reactor to polymerize the leftover monomer, because one of the qualities of the product is a maximum amount of unreacted monomer in the product. For the same logic, we have designed temperature profiles which are concave upwards, because we want to increase the temperature at the end of the reaction to facilitate the polymerization of the remaining polymer. And there's been a publication 3 years ago with colleagues from Dow on this topic. The result of it is that after doing 15 experiments, we were able to increase the productivity by 20%. So to some extent, if there was indeed a batch process for which there were no kinetic model, one could have done these 15 experiments in a pilot plant and come up with an optimal operation that would increase the productivity. So this is to some extent the aim and the use of the design of dynamic experiments. Let me move to the second topic of today's talk, is the establishment, the estimation of dynamic response surface models. And this is the schematic of the data that I showed you earlier, which is the viable cell density of a cell process, 30 experiments, and the model that was developed, which it is quite accurate. And keep in mind, this model is not, the model is not for one experiment at a time, it is for all the experiments and for all times. Let me talk about how this is being done. Let's say that you have a process, a reacting process, in which you measure the compositions of all the species at 1 hour, 2 hours, 14 hours, and you do 30 experiments. Well, one of the sources that existed before this contribution of ours is that you will estimate 14 different response surface models, one for the data collected at hour 1, one for the data collected in 2 hours, and the 14th such model for the data collected at the end of the batch. That will be the classical modeling of this data. And of course, instead of doing so, we will estimate a single DRSM model that will utilize all the experiments and all the measurements through the 14 hours of the experiment. So in order to do that, we do something that a posteriori is very simple, is we take the classical form of the model developed in the past, the response surface methodology, and we just generalize it to account for dynamics. So instead of dealing with one data point at one specific time, we're going to deal with all the data points at the different times. And we're able to do that when we generalize these coefficients of the model, these parameters of the model, and we transform them into parametric functions. So instead of having to estimate a value for beta 0, we now have to estimate a function, beta 0, a function of the time. And of course, the related beta i's and beta ij's and beta ii's. This is sort of a quadratic form of the RSM model, and this is the corresponding quadratic form of the DRSM model. How is it done? It is done by parametrizing these functions in terms of shifted Legendre polynomials again. And one more contribution that we have made is that it is better to parameterize them not with the time of the experiment, but with an exponential transformation of the time of the experiment. And this was mostly motivated by the fact that we know concentrations in reaction, such a reaction medium to some extent are either exponentially increasing or exponentially decreasing. This type of transformation enables us to have a more accurate model. And the parameters can be split into two types of parameters: global parameters, which is the overall polynomial order that we're going to use, how many such polynomials we're going to utilize for each of these parametric functions. And of course, what would be the value of this critical transformation time constant, which usually is between 30 and 70% of the batch time. Both of these things are estimated online from the appropriate software. Then the local parameters are these gamma coefficients, the proportional constants of the Sifted-Lezan polynomial for each of the vita parametric functions. And this is done through several ways. The latest one is utilizing lasso regression. But furthermore, after lasso regression is finished, the remaining gamma parameters who are left standing, you might say, are being tested whether they're significant or not. And if they're not significant, they are removed. The benefit of such a step is that we have a very frugal, a very model as far as the number of parameters. Here is some sets of data provided by Pfizer, which we modeled. This is an intermediate of an organic pharmaceutical reaction. And as you can see, the DRSM model is able to represent all 17 data and utilize all the 12 measurements per experiment. The confidence interval that you can see here is also quite narrow, indicating that the model is quite accurate. This utilizes a fifth order degree polynomial, and then the time constant is about 5.4 days from the 12 days that the experiments were collected. At the same time, we tested how the modeling methodology works if there were several data that they were missing. So for example, in the first experiment, instead of 12 data points, I only have 2. In the third experiment, I only have 2. In the fifth experiment, I have 5. And as you can see, the model is able to tell me how this composition would have varied with time, even though I only have 2 experiments. And this is possible because we are developing a model for all the experiments and all the data. So having missing experiments at a few of the missing data at a few of the experiments is not a kiss of death for the modeling methodology. In this case, the polynomial is a little bit smaller. Of course, this model is not as accurate as the previous one, which utilized all the data, but nevertheless, it is a very useful model. Here is another set of data provided to us by Merck. It involves 3 species. It has 5 factors. The set of experiments is split into 2 blocks. And at each experiment, there are 6 measurements that they are collected at unequal time intervals. Usually more measurements are collected at the initial stage of the reaction because that's where the largest change in the dynamics takes place, and at later on, the difference between time instances of measurement increases. This is a 1/4 fractional factorial design, which involves only 8 experiments. By analyzing the values of the factors, one can discover the aliasing structure. And this is the type of model that has been developed. Of course, here it is only the linear terms and only 2 of the several 2-term interaction terms because of the fractional character of the model. One of the things that they wanted us to determine is whether it makes a difference whether the data are being collected by a robotic device like the ones I showed you before, or whether they're collected manually. These are the two blocks in the data that have been, and we have determined that it makes no difference in accuracy of the model whether one uses the robotic device or not. The third and last part of what I want to expose you to is the fact that from data-driven models, the DRSM models, we can derive knowledge about the reaction, and we can discover the stoichiometry of the reaction. And this is the latest development. To some extent, what we want to do is we recognize how many species we have in the reaction. We will collect data during several experiments, as indicated here. From this data, we will develop DRSM models. And from these DRSM models, we are going to conclude what is the appropriate reaction network taking place. We claim that you might not necessarily get a single network which is the best fit into the data, but you're going to end up getting one or two, at most three networks that fit the data equally well. And of course, in these two or three networks, the true network will indeed be a member of. This, of course, is not the proof of any circumstance, but we've dealt with quite a few example cases that makes us confident that, that one can come up with the appropriate reaction network. So what we want to do, we want to collect composition data through a reaction, different experiments and different times, and we want to determine how many linearly independent reactions are present. And from that, we want to discover the stoichiometry, and at the same time, we want to estimate kinetics. Actually, the estimation of the kinetics will be a necessary tool for the discovery of the appropriate stoichiometry. So some recent results, which are yet unpublished, we've examined a case in which we had 11 species and 8 reactions, and we have discovered the correct stoichiometry after examining 44,448 possible reaction networks. How was it done? Well, we have not published that yet. Probably we'll publish it this year. But an earlier publication dealing with simpler and smaller problems has come out already at Industrial Engineering Chemistry Research. That's the special issue for our colleague Tunde Oginaki. So let's examine this simpler case and let's see what happens here. This is indeed the reaction network that we are going to simulate. And from that reaction network, we are going to collect composition data, and we're going to develop a DRSM model for each one of the 6 compositions measured. And I told you how to estimate such models. And then once we have these models, we can do something rather simple. We can take the derivative of these models. It's very easy to take the derivative of these models. And if you take the derivative, this will tell you the rate of change of this composition, rate of accumulation, rate of depletion of this composition at each experiment and at each time that you wish to calculate. And this is a very simple operation because then you differentiate these parametric functions vita. Once you have this data, then you can arrange the rate of appearance or disappearance of species A at different times. In the kth experiment, species B, species C, species D, E, and F, in this case, 6 of them, for each one of the experiments. Then they can take each of these experiments and stack them one under the other and have a big matrix RC, which collects data from all the experiments that you have dealt. And then you can do singular value decomposition, and the number of significant singular values is going to tell you how many linearly independent reactions are taking place in the medium. This, of course, is not a new discovery. Bonven and Ripin had talked about this problem, I guess, 33 years ago. But here, what Bonven and Ripin did then, after they did the singular value decomposition, then they tested candidate reactions to see if they are the ones present in the medium. What we do here is we do not need to have candidate reactions, but we try to examine all possible reactions that involve two reactants and two species, and they have a stoichiometric coefficient ranging between -1 and -2 and +2. So we collect all such reactions. We only keep those that satisfy the mass balance of the reaction. Here, the assumption is that we measure all the species taking place in the reaction, and that we know the molecular weight. And then we see which of these reactions are in agreement with the rate matrix RC utilizing Bonven and Ripin's target factor analysis. So for this specific example, 7 reactions qualified. Here they are. The true ones are the ones in red, but there were 4 additional reactions that one could not disqualify. The 4 additional reactions, obviously, they're linear combinations of the true 3 reactions, but at this stage, we do not know which of these 7 reactions are the true reactions taking place. So what we do next is we take these reactions and we develop 140 reaction networks, 3 reactions at a time. And 140 is nothing more than taking the number 7 and making combinations of the 7 reactions 3 at a time. Of those 140, 25 qualify because we have a certain number of filters that I'm not describing you at the moment. And then we have 25 networks that pass all the filters that we have imposed. One of the filters is that the reactions are linearly independent of each other. Another filter is that indeed with whatever is the initial compositions in our experiments, the reactions indeed can start and propagate, and that's not always true with all the candidate networks. And in essence, the methodology that we developed is as follows. We examine all the stoichiometric permutations. We impose mass balance to only retain a fraction of them. We use target factor analysis to see if they meet with the collected composition data and some additional filters. And then we have a combination of the remaining candidate reactions into networks of 3, 4, or 5, depending on how rich are the data. So we might have as many as n such networks for which we develop kinetic models. And when you develop kinetic models, you can see how well each of those kinetic models fit the data. And we've developed statistical comparisons, mostly F-tests, to see and judge whether a regression sum of square is statistically different from the next regression sum of squares until we arrive at the final networks. This is the overall methodology. And the last part, the comparative statistics that I say here, is very, very important in telling us which is the most accurate reaction network. And here is a test. If I ask you whether this reaction network is accurate, you look at the data, and I bet you 80% of you'll say yes, it is quite accurate. Visual comparison is not sufficient. This is not the best network. This is the second best. The plot that I'm giving you here are the same. The slides are just copies of each other. Here is the best, and this is statistically inferior by doing an F-test, and the p-value for this F-test is ridiculously small, implying that the certainty by which I can say that this network is better, that this network is worse than the second best, which I'll show you in the next slide, is almost with a certainty of 99.9999%. Here is the best network. And I repeat, you, by visual inspection, you probably are not going to distinguish the difference between these two networks. Yet the sum of squares are different, and the statistical comparison of the two networks is definitely without any doubt. So what did I tell you today? I talked to you about two novelties that of designing dynamic experiments and of estimating dynamic response surface models, which are generalizations of the classical DOE RSM tools in the literature, existing in the literature for the last 40 or 50 years. What I also told you is that from these data-driven models, we can identify the reaction stoichiometry. So from data-driven models, we can derive knowledge about what's happening in the reaction. This is useful because in many pharmaceutical reactions, and I'm sure in other circumstances, when people start doing experiments, they probably know what the main reaction is. They probably know what the main species are. But when they do the experiments and when they analyze all the compositions in the mixture, they come up with compositions that they do not know where the hell they came from. And thus discovering the stoichiometry is an important issue in such complex reactions, not because we're totally ignorant about stoichiometry, but because fine details of what's taking place in the reaction mixture, especially with byproducts and intermediates, might not be well known. So it was a pleasure speaking to you about this, and I'll be more than happy to answer any questions that you might have.
Well, thank you, Christos. That was a very motivating talk, and I can tell, just from many years of experience and working with collaborators in industry, but also academia, you have a rich set of data sets and experiences with batch processing. So fantastic work there. We're going to open it up now for questions. You can either unmute your microphone or you can ask a question in the chat window. So either one is okay. And I'll just start with a question here. It was interesting, the results. If you can go back to the slide where you showed let's see, let me get back to that one. The model-based and the optimal profiles, where you had the mode-based optimum was 65%. So that was the highest. And then the DoDE 1 optimum was 63.44. I just had a question about this, and it looked like as you went up on the number of experiments, you went up from 1, 5, and then 7. You expected the uncertainty to decrease as you went up to more experiments. Can you comment on that, though? It looked like it didn't get better with more experiments. It stayed about the same, but it was within the margin. The one with 5 had the highest uncertainty. Is that something you expected, or did you expect it to get lower uncertainty and closer to the optimum?
Well, you cannot really, there is some logic to it. I think that between DoDE 2 and DoDE 3, from 5 to 7, the uncertainty decreased. Okay. Now, the uncertainty increased when from the DoDE 1 to DoDE 2, because now I'm looking at a broader set of runs. I have in DoDE 1, I have one factor, which is the slope of the linear curve. In DoDE 2, I have 2 factors. So the domain over which the experiments are done is much wider, And moving from 3 to 5 experiments does not guarantee you that the model will be more accurate.
I think one of the powerful things about this slide is that, a deterministic optimization, where maybe you have a rate-based equations or other things and you apply an optimizer that gives you that solution up above. By doing this, the design of experiments and running these several cases, you also get the uncertainty associated with that. And I know from a lot of industrial processes, sometimes having a tighter confidence, tighter confidence window is better than even the optimum, because you can have repeatable processes and you know exactly how long those batches are going to take for scheduling or other things. So any thoughts on that?
John, your comment is quite interesting. The model-based optimum does not have uncertainty, and this is probably a complaint that I always have about knowledge-driven models. Knowledge-driven models have unknown parameters, and knowledge-driven models have their parameters estimated from experimental data. And when such parameters are being estimated, they ought to have some uncertainty related to it. And of course, if I had given my collaborator from CMU a plus or minus value for the kinetic parameters, he would have come up with a plus or minus value on the optimum.
Okay.
So the model-based optimum often has no uncertainty because of the wrong assumption that the parameters of the model have no uncertainty.
Mm-hmm.
So if I were to go back and say, hello, let's calculate the model-based optimum, but let's account for the kinetic parameters having usually 5% error, then there will be a plus or minus on the optimum calculated here. And maybe I should go and ask him to do that.
Fantastic. Okay, so I want to open up for additional questions from the audience. I have a whole slew of questions. Okay, Dominic, great. If you have a question.
Yes, it is Dominique Bonvin in Lausanne. Hi, Christos.
Hello, Dominique.
Hi, everyone. Very, very nice talk. Very interesting. A good summary of very important work that you have done throughout the years. I have several questions, but I will probably limit myself to 2 questions. The first one regards the 2 concepts of DODE and DRSM. So those are very interesting concepts. But to me, throughout the years, I've always thought these 2 concepts could come together. And looking at your presentation today, it's tonight for me here in Lausanne, but today for you, looking at your presentation, it's clear to me that these 2 concepts should come together as one single concept that you may call, for example, data-driven dynamic modeling or data-driven dynamic modeling or data-driven dynamic optimization. So my question is, why do you always keep them separate? Because to design the DRSM models, you need to have dynamic experiments.
No.
Yes?
No.
No? Okay.
No. The data that I showed you, let's say this data from the cell process with one company that I'm collaborating with, these data are not there from DOE data. They only change the temperature and pH and the initial cell culture, but they did not change the temperature with time. They did not change the pH with time.
Okay.
So you can have a DRSM model without, by only doing DOE experiments, but collecting time resolved data.
Okay, I see. Okay.
And there is a reluctance from industrial people to do dynamic experiments because they might not have the equipment, let's say, to change the temperature with some appropriate controller to change the temperature of the reactor linearly.
Okay.
or quadratically. I found more resistance in doing dynamic experiments than in developing dynamic DRSM models.
Okay. Okay. Sorry, I missed that point, but that's a very good point. Yeah. I mean, here your inputs were actually constant. You had constant temperature, constant pH or whatever. Or,
so you can combine the two. There is no question about it.
Yeah, certainly you can combine them. Yeah.
But you can have them separate too, right? You can do design of dynamic experiments and only calculate things at the end.
Okay. And what is your preference? Would you rather change the input with time or not?
That's a difficult question. I think that from what we have published so far, in order to be able to optimize the process and discover whether it will be better run by changing the temperature, yeah, you have to do dynamic experiments.
Okay.
I probably don't want to speculate on I think that by dealing with, for example, in this case with the cell process, I was able to pull a rabbit out of my hat, so to speak, and recommend that you can see that in this cell process, there are two segments in a cell process. The first segment is to increase the number of cells, and the second segment is to increase the product that's been made. So in this process, there is a paper in the works where we took this data and we took the DRSM model, and we've come up with the suggestion that you operate from first day until the fourth under a given pH in order to maximize this peak, the viable cell density at day 4, and then a different pH in order to increase the product. Okay. And this increased the product composition almost by 20%. But again, I'm moving off script here because we haven't published that yet. Okay, still room for investigation. Yeah, if I may, I would have a second question. Do I have time for that?
Sure.
Okay. My second question regards the last part of your talk regarding stoichiometric and kinetic investigation. It's very well done. But in your example, if I remember correctly, you have 6 species. And the approach you demonstrated used a measurement of all species. Now, if you look at, if you consider, let's say, the batch chemical industry, there are often a large number of species. 6 is already a fair number, but very often you cannot measure all 6 species, all species. So how do you deal with missing, that is, unmeasured species, species for which you don't have measurements? In that example, in that given, to be specific, in that given example, for example, if you were able to measure only, let's say, 3 species, would you have been able to come up with a stoichiometry?
The answer is yes and no. For example, we have started looking at this situation, which is indeed taking place. For example, in this example, D is water.
Okay.
And you won't be able to measure water even if the medium was not the reaction medium was not water.
Okay. Yeah.
So I think from our point of view, you need to know all the species present. That's a requirement. If you're missing one species, then you can do the mass balance. So you need to know that there is water being involved in the reaction.
Okay.
In this case, because we've done the calculation, if you do not measure water, you can indeed back calculate the water, because keep in mind here you have 6 species.
Yes.
And there are only 3 reactions. So the species are moving in a 3-dimensional space. So I can afford not to measure water, utilize the other species, and back calculate the extent of the reaction without the water. And for the candidate reaction network, I can back calculate the not measured water composition.
Okay.
So in reality, I can afford to have only 3 measurements, but not any 3 measurements.
Is there any relationship between the minimum number of measurements you need to have and the number of independent reaction you expect in your?
The minimum number of measurements ought to be the number of reactions, right?
Well, if you have fewer than the number of reactions, you won't be able to do anything. But,
correct.
Yeah. But in addition, you have noise, and you have a lot of uncertainty, and you have a large number of possible reactions. So it may not be as easy. So
Dominique, let's say that this is still an open problem, but it is not a lost case. You can do what we did here if you do not measure one species, and in work that is presently not totally completed, we have especially in that big network with 44,000 networks that we examined, it is possible to not to measure 2 or 3 of the 11 species.
Okay. Good. Well, I look forward to your future results. Thank you.
Well, fantastic. Well, we're about out of time now. We'd just like to thank Christos one more time for the excellent presentation, and also congratulations on the CAS Division Award for 2022. It's certainly well-deserved from a lifetime of service to the process systems engineering community, and particularly with the Computing and Systems Technology Division within AIChE. So congratulations on that award, Christos, and excellent presentation today.
Thank you, John. Thank you.